Introduction to quantum entanglement. Quantum entanglement is a phenomenon that lies at the heart of quantum mechanics, a branch of physics that describes the behavior of matter and energy at small scales. The concept of entanglement challenges our classical intuitions about the separability and independence of distant objects, unveiling a reality that is far more interconnected than it appears. This essay provides an overview of quantum entanglement, its historical context, fundamental principles, and its implications for our understanding of the universe. Historical background. The origins of quantum entanglement trace back to the early 20th century, during the development of quantum theory. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper introducing what is now known as the Einstein-Podolsky-Rosen EPR paradox. They aimed to demonstrate that quantum mechanics could not be a complete theory because it allowed for non-local interactions between entangled particles. According to their interpretation, if two particles are entangled, measuring the state of one particle instantaneously determines the state of the other, regardless of the distance separating them. This spooky action at a distance, as Einstein called it, seemed to violate the principle of locality, which states that objects are only directly influenced by their immediate surroundings. Fundamental principles of quantum mechanics. To understand quantum entanglement, one must first grasp several key principles of quantum mechanics. At its core, quantum mechanics describes how particles, such as electrons and photons, behave in ways that differ significantly from classical physics. Superposition. Quantum particles can exist in multiple states simultaneously until measured. For example, a particle can be in a state of both spin up and spin down until an observation collapses this superposition into one definitive state. Measurement. The act of measuring a quantum state alters the state itself. This phenomenon is famously illustrated by the thought experiment known as Schrödinger's cat, where a cat is simultaneously alive and dead until observed. Entanglement. When two or more particles become entangled, their quantum states become interdependent. The measurement of one particle instantly influences the state of the other, even if they are separated by vast distances. This correlation persists regardless of the physical separation, leading to the non-local nature of quantum mechanics. The nature of entanglement. Entangled particles are described by a joint quantum state that cannot be factored into individual states. For instance, consider two entangled photons, A and B. If we measure the polarization state of photon A and find it to be vertical, photon B will instantly be found to have horizontal polarization upon measurement, regardless of the distance between them. This instantaneous correlation has been experimentally verified in numerous studies, reinforcing the concept of entanglement as an essential feature of quantum systems. Experimental verification. The first experimental evidence for quantum entanglement emerged in the 1970s when physicist Alain Aspect conducted a series of experiments that tested the predictions of quantum mechanics against those of classical physics. Entanglement enables parallel processing, allowing multiple computations to occur simultaneously, which could lead to breakthroughs in complex problem-solving. In quantum cryptography, entanglement is harnessed to create secure communication channels that are theoretically immune to eavesdropping. The security arises from the fact that any attempt to measure or intercept the entangled states would disturb them, alerting the communicating parties to potential breaches. Moreover, entanglement raises fundamental questions about the nature of reality itself. It challenges our classical intuitions about separability and locality, suggesting that the universe is more interconnected than it appears. Philosophers and scientists alike grapple with the implications of entanglement, pondering issues related to determinism, realism, and the very fabric of spacetime. Conclusion. In summary, Quantum entanglement is a cornerstone of quantum mechanics that reveals the intricate connections between particles at a fundamental level. It arose from historical debates about the completeness of quantum theory and has been experimentally validated through numerous studies. As we delve deeper into the implications of entanglement, we unlock new technologies and confront profound philosophical questions that shape our understanding of the universe. The exploration of quantum entanglement is not merely an academic pursuit. It is a journey into the very nature of reality, where the boundaries of space, time, and information blur in intriguing ways. As research continues to unfold, the potential applications of entanglement in communication, computing, and beyond promise to reshape our technological landscape and challenge our perceptions of the cosmos. Quantum entanglement in space. Quantum entanglement, a phenomenon that allows particles to be interconnected regardless of the distance separating them, has profound implications for our understanding of the universe, particularly in the context of space. This essay explores the nature of quantum entanglement in space, its experimental verification, its applications in space-based technologies, and its potential future implications for communication, exploration, and our understanding of the cosmos. The nature of quantum entanglement. Quantum entanglement occurs when two or more particles become correlated in such a way that the state of one particle is directly related to the state of another, regardless of the distance between them. This non-local property challenges classical intuitions about separability and locality, suggesting a deep interconnectedness in the fabric of reality. When two particles are entangled, their quantum states are described by a single wave function. This means that measuring one particle instantly influences the other particle's state, even if they are light years apart. This phenomenon was famously illustrated by the Einstein-Podolsky-Rosen EPR paradox, which questioned whether quantum mechanics could be a complete theory, given its implications for instantaneous interactions across vast distances. Experimental verification in space. The exploration of quantum entanglement in space has gained momentum in recent years, with several key experiments demonstrating its viability. One of the most notable experiments is the use of satellites to test entanglement over long distances. In 2017, China's Mikius satellite successfully transmitted entangled photon pairs over a distance of 4,600 kilometers, establishing a new frontier in quantum communication. These experiments have not only tested the predictions of quantum mechanics, but also provided insights into the fundamental nature of reality. By demonstrating entanglement over vast distances, scientists have gained a better understanding of how quantum mechanics operates on cosmic scales, providing a bridge between quantum theory and relativity. Applications in space communication. The implications of quantum entanglement for communication are profound. Quantum key distribution, QKD, is one of the most promising applications of entanglement in secure communications. By utilizing entangled particles, QKD enables two parties to generate a shared secret key that is theoretically immune to eavesdropping. Any attempt to intercept the entangled particles would disturb their states, alerting the communicating parties to potential breaches. Space-based quantum communication networks could revolutionize global communication by providing secure channels that are resistant to hacking and eavesdropping. Moreover, these networks could facilitate instantaneous communication across vast distances, overcoming the limits imposed by classical communication methods. For example, in a future scenario where quantum satellites are deployed, they could create a global network of entangled particles that ensures secure communication between Earth and space missions. This capability would be invaluable for interplanetary communication, providing a means to transmit data securely between distant spacecraft and mission control on Earth. The role of entanglement in space exploration. Quantum entanglement also has potential applications in space exploration. One promising area is in the development of quantum sensors that could enhance our ability to measure gravitational waves, dark matter, and other cosmic phenomena. Entangled particles can be used to create highly sensitive detectors that outperform classical sensors, enabling scientists to probe the universe's mysteries with greater precision. Additionally, entanglement may play a role in the quest for a deeper understanding of the fundamental laws of physics. By studying entangled particles in space, researchers can investigate the interplay between quantum mechanics and general relativity, potentially uncovering new insights into the nature of space-time and the universe's fundamental structure. Future implications and challenges. While the potential applications of quantum entanglement in space are exciting, there are also significant challenges that must be addressed. One major hurdle is the issue of decoherence, which refers to the loss of quantum coherence due to interactions with the environment. In space, the harsh conditions and radiation can disrupt the delicate quantum states of entangled particles, posing challenges for maintaining their entanglement over long distances. Researchers are actively exploring methods to mitigate decoherence, such as using advanced materials and technologies that can shield entangled particles from environmental disturbances. Moreover, developing robust quantum repeaters could help extend the distance over which entanglement can be maintained, enabling the establishment of reliable quantum communication networks. Another challenge is the integration of quantum technologies with existing classical systems. As we move toward a future where quantum communication becomes viable, ensuring compatibility with classical networks will be essential. This integration will require interdisciplinary collaboration across fields such as physics, engineering, and computer science. Philosophical considerations. The exploration of quantum entanglement in space also raises profound philosophical questions about the nature of reality and our understanding of the universe. The non-locality of entanglement challenges classical notions of causality and separability, prompting us to reconsider our fundamental assumptions about how the universe operates. As we delve deeper into the implications of entanglement, we confront questions about determinism, the nature of information, and the interconnectedness of all things. These philosophical inquiries are not merely academic. They have the potential to reshape our understanding of the cosmos and our place within it. Conclusion: quantum entanglement in space represents a frontier of scientific exploration that holds promise for revolutionizing communication, enhancing our understanding of the universe, and unlocking new technologies. Through experimental verification and innovative applications, scientists are beginning to harness the power of entanglement for practical purposes, paving the way for secure quantum communication networks and advanced space exploration. As we continue to investigate the intricacies of quantum entanglement, we must also grapple with the philosophical implications of this phenomenon. The interconnectedness revealed by entanglement challenges our classical intuitions and invites us to reconsider our understanding of reality itself. In summary, quantum entanglement in space is not just a fascinating scientific phenomenon. It is a gateway to new technologies and profound insights into the nature of the universe. As research in this area progresses, we stand on the brink of a new era of exploration and understanding, one that promises to reshape our relationship with the cosmos and our understanding of the fundamental laws that govern it. Implications of quantum entanglement for communication. Quantum entanglement, a fundamental phenomenon in quantum mechanics, has profound implications for communication technologies. By enabling instantaneous correlations between entangled particles, quantum entanglement challenges classical views of information transmission and opens new avenues for secure, efficient, and revolutionary communication methods. This essay explores the implications of quantum entanglement for communication, focusing on quantum key distribution, advancements in quantum networks, potential applications in long-distance communication, and the broader impact on information security and technology. Understanding quantum entanglement in communication. At its core, quantum entanglement refers to the peculiar linkage between particles such that the state of one particle is directly correlated with the state of another, regardless of the distance separating them. When two particles become entangled, measuring the state of one instantaneously determines the state of the other. This non-local property forms the basis for various applications in communication. In classical communication, information is transmitted through signals that can be intercepted or altered by eavesdroppers. Quantum communication, leveraging the principles of quantum mechanics, allows for fundamentally different approaches to transmitting information, particularly through quantum key distribution, QKD. Quantum key distribution, QKD. Quantum key distribution is one of the most promising applications of quantum entanglement in secure communication. QKD enables two parties to generate a shared secret key for encrypting messages in a way that is theoretically immune to eavesdropping. The security of QKD arises from the principles of quantum mechanics. If an eavesdropper attempts to intercept or measure the entangled particles, the quantum states are disturbed, alerting the legitimate users to the presence of an intruder. One of the most well-known QKD protocols is the BB84 protocol, proposed by Charles Bennett and Gilles Broussard in 1984. In this protocol, entangled photons are used to create a shared key, which can then be used for secure communication. The fundamental advantage of QKD lies in its ability to detect any eavesdropping attempts, ensuring the integrity and confidentiality of the transmitted information. Several experimental implementations of QKD have demonstrated its feasibility in real-world scenarios. Notably, quantum key distribution has been successfully tested over long distances, including satellite-based QKD, which allows for secure communication across continents. These advancements mark a significant step forward in the realm of secure communication, addressing the vulnerabilities of classical cryptographic methods. Advancements in quantum networks. The development of quantum networks represents another significant implication of quantum entanglement for communication. Quantum networks are designed to connect quantum devices, enabling the transmission of quantum information across distances. By utilizing entangled particles, quantum networks can facilitate secure communication channels that surpass the capabilities of classical networks. Quantum repeaters play a crucial role in extending the distances over which entanglement can be maintained. These devices utilize entanglement swapping and purification techniques to create long-range entangled states. By overcoming the challenges of decoherence and signal loss, quantum repeaters enable the establishment of reliable quantum communication links. The construction of a global quantum internet is a long-term goal for researchers and technologists. A quantum internet would allow for the seamless integration of quantum communication technologies with existing classical infrastructures, providing a hybrid system that capitalizes on the advantages of both paradigms. This internet would not only facilitate secure communication, but also enable the development of distributed quantum computing and advanced applications in cryptography and sensing. Long-distance communication and space applications. Quantum entanglement has profound implications for long-distance communication, particularly in the context of space exploration. Traditional communication methods face significant challenges when transmitting signals across vast distances, such as the time delays associated with light travel and the potential for signal degradation. Quantum communication, on the other hand, offers a means to overcome these limitations. In space missions, the ability to establish secure and instantaneous communication links between spacecraft and mission control is crucial. Quantum entanglement can facilitate the transmission of information in a way that is both efficient and secure. For instance, entangled photons can be used to create communication channels between satellites, allowing for secure data exchange and real-time communication with Earth. Recent advancements in satellite-based quantum communication have demonstrated the feasibility of transmitting entangled states over long distances. China's Mikius satellite, launched in 2016, successfully transmitted entangled photon pairs between ground stations, paving the way for future space-based quantum communication networks. These developments hold the potential to revolutionize how we communicate in space and could enhance the capabilities of future interplanetary missions. Impact on information security. The implications of quantum entanglement for communication extend to information security, a critical concern in our increasingly digital world. As cyber threats continue to evolve, the need for robust security measures becomes paramount. Quantum communication technologies, particularly QKD, offer a solution that is inherently secure against many conventional hacking techniques. Unlike classical cryptographic methods, which rely on mathematical algorithms that can potentially be broken by quantum computers, quantum communication is based on the laws of quantum mechanics. This fundamental difference means that quantum communication can provide a level of security that classical systems cannot match. As quantum computers become more powerful, the need for quantum secure communication will grow, making quantum entanglement an essential aspect of future information security strategies. Challenges and limitations. Despite the promising implications of quantum entanglement for communication, several challenges remain. One of the primary obstacles is the issue of decoherence, which refers to the loss of quantum coherence due to interactions with the environment. In practical applications, maintaining entangled states over long distances is challenging, as environmental factors can disrupt the delicate quantum states. Researchers are actively working on developing technologies to mitigate decoherence, such as advanced materials that can shield entangled particles from environmental disturbances. Additionally, improving the efficiency of quantum repeaters and enhancing the reliability of quantum networks are crucial steps toward realizing the full potential of quantum communication. Another challenge lies in the integration of quantum communication technologies with existing classical systems. As quantum communication becomes more prevalent, ensuring compatibility with classical networks will be essential for a smooth transition to a hybrid communication infrastructure. Conclusion: quantum entanglement has profound implications for communication, revolutionizing the way we transmit information and ensuring secure channels in an increasingly digital world. With applications in quantum key distribution, advancements in quantum networks, and long-distance communication capabilities, quantum entanglement represents a transformative force in the field of communication technology. As we continue to explore the potential of quantum entanglement, addressing the challenges of decoherence and integration with classical systems will be crucial. The development of a global quantum internet and the realization of secure communication channels in space will pave the way for a new era of information exchange. In an age where information security is paramount, The unique properties of quantum entanglement offer a promising solution to the vulnerabilities of classical communication methods. As research in this field progresses, we stand on the brink of a communication revolution that could reshape how we connect, share, and interact in the digital landscape. The future of communication lies in the quantum realm, where the principles of entanglement challenge our classical intuitions and open new frontiers in technology and understanding. Implications of quantum entanglement for teleportation. Quantum teleportation, a phenomenon that arises from the principles of quantum entanglement, represents one of the most intriguing and groundbreaking advances in modern physics. Unlike the teleportation depicted in science fiction, which implies the instantaneous transportation of objects from one location to another, quantum teleportation involves the transfer of quantum states between particles without the physical transfer of the particles themselves. This essay explores the implications of quantum entanglement for teleportation, detailing the mechanics behind it, potential applications, challenges, and its broader significance for our understanding of information and reality. Understanding quantum teleportation. Quantum teleportation is rooted in the principles of quantum mechanics, particularly quantum entanglement and superposition. To grasp how teleportation works, it is essential to understand the key components involved in the process. Quantum states. A quantum state describes the properties of a quantum system, such as the position, momentum, or spin of a particle. Unlike classical states that are well-defined until measured, quantum states can exist in superpositions, meaning they can represent multiple possibilities simultaneously. Entanglement. As previously discussed, entanglement is a phenomenon in which two or more particles become correlated in such a way that the state of one particle is linked to the state of another, regardless of the distance between them. When particles are entangled, measuring one particle instantaneously affects the state of the other. The teleportation process. Quantum teleportation involves three main steps. Preparation. Two parties, often referred to as Alice and Bob, share a pair of entangled particles, which serve as a quantum channel. Measurement. Alice performs a joint measurement on her particle, the one to be teleported, and her half of the entangled pair. This measurement entangles her particle with the entangled pair, collapsing the quantum state into one of several possible outcomes. Commutation and reconstruction. Alice sends the results of her measurement to Bob through classical communication. Based on this information, Bob performs a specific operation on his half of the entangled pair, reconstructing the original quantum state of Alice's particle. It is crucial to note that quantum teleportation does not involve the transfer of matter. Instead, it transfers the information contained in the quantum state. This process has been experimentally demonstrated with various quantum systems, including photons and atoms, marking a significant milestone in quantum information science. Applications of quantum teleportation. The implications of quantum teleportation are profound, with potential applications across several fields. Quantum computing. Quantum teleportation plays a pivotal role in the development of quantum computers. By enabling the transfer of quantum states between qubits, quantum bits, teleportation can facilitate operations that enhance computational efficiency. It allows for the creation of distributed quantum computing systems, where qubits located in different physical locations can be manipulated as if they were part of a single system. Quantum communication. The ability to teleport quantum states enhances secure communication channels. As previously mentioned, quantum key distribution (QKD) relies on the principles of quantum mechanics to ensure secure communication. Quantum teleportation can complement QKD by enabling the transfer of quantum information securely, allowing for more complex communication protocols. Quantum networks. The concept of a quantum internet, where quantum information is transmitted seamlessly across networks, heavily relies on quantum teleportation. By using teleportation to transfer quantum states between nodes in a network, researchers aim to create robust quantum communication systems that can operate over long distances. Quantum cryptography. Beyond secure communication, quantum teleportation can enhance cryptographic protocols by allowing for the transfer of cryptographic keys and states without the risk of interception. This property could revolutionize how sensitive information is transmitted, ensuring that only authorized parties can access it. Challenges in quantum teleportation. Despite its promising potential, quantum teleportation faces several challenges that must be addressed for practical applications. Decoherence. One of the primary obstacles to implementing quantum teleportation in real-world scenarios is the phenomenon of decoherence. Quantum states are fragile and can easily lose their coherence due to interactions with the environment. This loss of coherence can render the teleportation process ineffective, as the original quantum information may be corrupted or lost. Scalability. While quantum teleportation has been successfully demonstrated in laboratory settings, scaling the process for practical use in quantum networks poses significant challenges. Developing robust quantum repeaters and entanglement distribution systems is essential for ensuring the reliability of long-distance teleportation. Classical communication. Quantum teleportation relies on classical communication to transfer measurement results. This requirement introduces a time delay in the process, as the classical information must be transmitted before the state can be reconstructed. Overcoming this limitation is crucial for achieving faster and more efficient teleportation protocols. Broader implications for our understanding of reality. The exploration of quantum teleportation raises profound philosophical questions about the nature of reality, information, and causality. Information versus matter. Quantum teleportation challenges conventional notions of information and materiality. The fact that quantum states can be transferred without the physical movement of particles prompts us to reconsider our understanding of what constitutes an object or a state of. Non-locality and causality. The non-local nature of entanglement, which underpins quantum teleportation, challenges classical intuitions about causality and separability. The instantaneous correlation between entangled particles suggests a level of interconnectedness that defies classical explanations, prompting deeper inquiries into the structure of space-time and the nature of reality. The nature of measurement. Quantum teleportation highlights the role of measurement in quantum mechanics. The act of measuring a quantum state not only reveals information, but also influences the system, collapsing it into a definitive state. This interplay between observation and reality raises philosophical questions about the observer's role in shaping the universe. Conclusion. Quantum teleportation, rooted in the principles of quantum entanglement, represents a significant advancement in our understanding of quantum mechanics and its applications. With potential implications for quantum computing, secure communication, and the development of quantum networks, teleportation offers a glimpse into a future where information is transmitted in fundamentally new ways. While challenges such as decoherence and scalability remain, ongoing research continues to push the boundaries of what is possible. The broader implications of quantum teleportation extend beyond technology, prompting profound questions about the nature of reality, information, and the interconnectedness of the universe. As we delve deeper into the intricacies of quantum teleportation, we not only unlock new technological possibilities, but also engage with fundamental philosophical inquiries that could reshape our understanding of the cosmos. Quantum teleportation is not just a fascinating scientific phenomenon. It is a gateway to exploring the very fabric of reality and our place within it. The future of quantum teleportation promises to be an exciting journey, with the potential to redefine our relationship with information, communication, and the universe itself. Technological advancements in quantum entanglement. Quantum entanglement, a cornerstone of quantum mechanics, has catalyzed numerous technological advancements that promise to reshape various fields, from computing and communication to sensing and cryptography. As researchers continue to explore the intricate properties of entanglement, we are witnessing the emergence of innovative technologies that leverage this phenomenon. This essay delves into recent advancements in quantum technology, their potential applications, and the challenges that lie ahead as we strive to harness the power of quantum entanglement. 1. Quantum computing. One of the most significant technological advancements stemming from quantum entanglement is the development of quantum computers. Unlike classical computers, which process information in bits, zeros and ones, quantum computers utilize qubits, quantum bits that can exist in superpositions of states. This ability allows quantum computers to perform certain calculations exponentially faster than their classical counterparts. 1.1. Entangled qubits. Entangled qubits form the basis of quantum computing's power. By creating networks of entangled qubits, researchers can develop quantum algorithms that solve complex problems, such as factoring large numbers or optimizing systems, much more efficiently than classical algorithms. Prominent quantum algorithms, such as Shor's algorithm for factoring and Grover's algorithm for searching unsorted databases, rely on the properties of entanglement to achieve their speed. 1.2. Quantum supremacy. In 2019, Google claimed to have achieved quantum supremacy with its quantum processor, Sycamore, which performed a specific computation in 200 seconds that would take the most advanced classical supercomputers approximately 10,000 years to complete. This milestone highlights the potential of quantum computing to revolutionize fields such as cryptography, materials science, and drug discovery. 2. Quantum communication. Quantum communication technologies leverage entanglement to create secure channels for transmitting information. These advancements are particularly significant in the context of cybersecurity, where traditional encryption methods face threats from quantum computing. 2.1. Quantum key distribution, QKD. Quantum key distribution is one of the most promising applications of quantum communication. QKD allows two parties to generate a shared secret key for secure communication. The security of QKD stems from the laws of quantum mechanics. Any attempt to measure or intercept the entangled particles will disturb their states, alerting the legitimate users to potential eavesdropping. Several QKD protocols, including the BB84 and E91 protocols, have been successfully implemented in laboratory settings and in real-world applications. Satellite-based QKD, such as the experiments conducted with China's Mikia satellite, has demonstrated the feasibility of secure quantum communication over long distances, paving the way for global quantum communication networks. 2.2. Quantum repeaters. Quantum repeaters are essential for extending the range of quantum communication. These devices utilize entanglement swapping and purification techniques to maintain the integrity of entangled states over long distances. By enabling the reliable transmission of quantum information, quantum repeaters are crucial for building large-scale quantum networks. 3. Quantum sensing. Quantum entanglement also has significant implications for sensing technologies. Quantum sensors leverage the sensitivity of entangled states to measure physical quantities with unprecedented precision. 3.1. Applications in metrology. Quantum sensors are poised to revolutionize metrology, the science of measurement. For instance, atomic clocks, which utilize the vibrations of atoms to measure time, can achieve remarkable accuracy through entanglement. These advancements have applications in global positioning systems, GPS, telecommunications, and fundamental physics. 3.2. Gravitational wave detection. Entangled states can enhance the sensitivity of gravitational wave detectors, such as LIGO, Laser Interferometer Gravitational Wave Observatory. By utilizing squeezed light, an entangled state of photons, researchers can reduce quantum noise and improve the accuracy of measurements, enabling the detection of weaker gravity. Beyond QKD, quantum cryptography encompasses various protocols that aim to secure communication against potential threats. 4.1. Device-independent QKD. Device-independent QKD protocols aim to eliminate the need for trust in the devices used for quantum communication. By relying solely on the observed correlations of entangled states, these protocols ensure security even if the devices are potentially compromised. This advancement is crucial for increasing the robustness of quantum cryptographic systems. 4.2. Post-quantum cryptography. As quantum computers become more powerful, traditional cryptographic methods are at risk of being rendered obsolete. Post-quantum cryptography seeks to develop new cryptographic algorithms that remain secure against quantum attacks. While not directly reliant on entanglement, the integration of quantum principles into cryptographic systems represents a significant step toward a secure digital future. 5. Challenges and future directions. Despite the promising advancements in quantum technologies, several challenges remain that must be addressed for practical applications. 5.1. Decoherence and error correction. Decoherence, the loss of quantum coherence due to interactions with the environment, poses a significant challenge for quantum systems. Maintaining the integrity of entangled states over time is crucial for the success of quantum computing and communication. Researchers are actively developing error correction techniques and advanced materials to mitigate the effects of decoherence. 5.2. Scalability. Scaling quantum technologies for widespread use is another challenge. While small-scale quantum systems have demonstrated remarkable capabilities, building large-scale quantum computers and networks requires significant advancements in engineering and infrastructure. 5.3. Interdisciplinary collaboration. The development of quantum technologies necessitates collaboration across multiple disciplines, including physics, engineering, computer science, and cryptography. Fostering interdisciplinary partnerships will accelerate progress and innovation in the quantum realm. Conclusion: the technological advancements driven by quantum entanglement are reshaping the landscape of computing, communication, sensing, and cryptography. From quantum computing and secure communication to precision measurement and cryptographic security, the implications of quantum entanglement are profound and far-reaching. As researchers continue to explore the intricacies of quantum mechanics, addressing the challenges of decoherence, scalability, and interdisciplinary collaboration will be essential for realizing the full potential of quantum technologies. The journey into the quantum realm is just beginning, and the possibilities are vast. As we unlock the secrets of quantum entanglement, we stand on the threshold of a new technological era, one that promises to revolutionize our understanding of information, security, and the very nature of reality itself. Ethical and philosophical considerations of quantum entanglement. Quantum entanglement, a fundamental phenomenon of quantum mechanics, challenges our classical understanding of reality, prompting not only scientific inquiry, but also profound ethical and philosophical considerations. As we delve deeper into the implications of quantum entanglement in areas such as communication, computing, and information security, it is essential to examine the ethical dilemmas and philosophical questions that arise. This essay explores the ethical and philosophical dimensions of quantum entanglement, focusing on its implications for privacy, security, the nature of reality, and the future of technology. 1. Privacy and security in quantum communication. 1.1. The promise of quantum security. Quantum communication technologies, particularly quantum key distribution, QKD, offer revolutionary advancements in secure information transfer. By leveraging the principles of quantum mechanics, QKD provides a framework for secure communication that is theoretically immune to eavesdropping. This capability raises critical ethical questions regarding privacy and the right to secure communication. 1.2. Ethical implications of surveillance. As quantum communication technologies become more prevalent, they may be integrated into surveillance systems, raising ethical concerns about the balance between security and privacy. Governments and corporations could potentially exploit these technologies to monitor communications more effectively, leading to increased surveillance and potential invasions of privacy. The ethical implications of such practices necessitate a careful examination of the boundaries of acceptable surveillance, informed consent, and the protection of individual rights. 1.3. Access and inequality. The deployment of quantum communication technologies may exacerbate existing inequalities in access to information and technology. If only certain individuals or groups can utilize advanced quantum communication systems, a digital divide could emerge, reinforcing socioeconomic disparities. Ethical considerations must address how to ensure equitable access to these technologies, promoting inclusivity and preventing discrimination. 2. The nature of reality and information. 2.1. Quantum non-locality and reality. Quantum entanglement challenges classical notions of locality and separability, suggesting a level of interconnectedness in the universe that defies traditional understandings. The phenomenon of non-locality raises philosophical questions about the nature of reality itself. If particles can instantaneously affect one another, regardless of distance, what does this imply about causality and the fabric of spacetime? 2.2. Implications for determinism. The implications of quantum entanglement extend to philosophical discussions of determinism and free will. Classical physics operates under deterministic principles, where the future state of a system can be predicted based on its initial conditions. However, the probabilistic nature of quantum mechanics and the randomness of measurement outcomes challenge these deterministic views. This raises questions about the extent to which free will exists and how our understanding of choice may be influenced by quantum phenomena. 2.3. The observer effect. The role of the observer in quantum mechanics introduces additional philosophical questions. In quantum entanglement, the act of measurement influences the state of the system, leading to the observer effect. This raises ethical considerations regarding the role of human perception and consciousness in shaping reality. If our observations alter the state of quantum systems, what responsibilities do we have as observers? The implications for scientific inquiry and the ethical treatment of experimental subjects must be considered. 3. Future technologies and ethical responsibility. 3.1. The role of quantum technologies in society. As quantum technologies continue to develop, their integration into everyday life raises ethical questions about responsibility and accountability. The potential for quantum computers to break existing cryptographic systems poses risks to data security and privacy. Ethical considerations must guide the responsible development and deployment of these technologies to mitigate potential harm. 3.2. Regulation and governance. The rapid advancement of quantum technologies necessitates the establishment of regulatory frameworks to ensure ethical practices. Policymakers must grapple with questions about how to regulate emerging technologies while fostering innovation. Balancing the promotion of scientific progress with ethical considerations is crucial to ensuring that quantum technologies are developed and applied responsibly. 3.3. Global cooperation. Given the global implications of quantum technologies, international cooperation is essential. Ethical considerations must transcend national boundaries to address the potential for misuse and inequality. Collaborative efforts among nations, researchers, and industry stakeholders can promote the responsible development of quantum technologies and ensure that their benefits are shared equitably. 4. Philosophical questions about knowledge and reality. 4.1. The nature of knowledge. Quantum entanglement raises profound questions about the nature of knowledge itself. If information can be instantaneously transmitted between entangled particles, what does this mean for our understanding of knowledge as a construct? The implications for epistemology, the study of knowledge, are significant, as they challenge traditional notions of how we acquire and validate knowledge. 4.2. Reality as a construct. The interconnectedness revealed by quantum entanglement prompts philosophical inquiries into the nature of reality. Is reality a fixed construct, or is it shaped by our perceptions and interactions? The implications for metaphysics are profound, as quantum mechanics suggests that reality may be more fluid and relational than previously understood. 4.3. Ethical implications of knowledge acquisition. As our understanding of quantum entanglement grows, ethical questions arise regarding the acquisition and application of knowledge. Researchers and technologists must consider the implications of their discoveries, especially when it comes to potential misuse or harmful applications. The ethical responsibility to use knowledge for the greater good must guide scientific inquiry and technological advancement. Conclusion. The ethical and philosophical considerations surrounding quantum entanglement are as profound as the scientific implications of this phenomenon. As we explore the intricacies of quantum mechanics and its applications, it is essential to engage in critical discussions about privacy, security, the nature of reality, and the responsibilities that accompany technological advancements. Quantum entanglement challenges our classical intuitions and invites us to reconsider fundamental questions about existence, knowledge, and interconnectedness. As we advance into the quantum era, the ethical frameworks and philosophical inquiries we establish will shape not only the future of quantum technologies, but also our understanding of ourselves and our place in the universe. In navigating the ethical landscape of quantum entanglement, we must strive for a balance between innovation and responsibility, ensuring that the benefits of these technologies are shared equitably, and that our pursuit of knowledge is guided by ethical principles. The journey into the quantum realm is not merely a scientific endeavor. It is a philosophical exploration that invites us to reflect on the deeper meanings of reality, information, and our interconnected existence. Conclusion. The multifaceted implications of quantum entanglement. Quantum entanglement stands as one of the most fascinating and perplexing phenomena in modern physics, offering profound insights into the nature of reality and the interconnectedness of the universe. As we have explored throughout this essay, the implications of quantum entanglement extend beyond the realm of theoretical physics, impacting various fields such as communication, computing, sensing, and cryptography. Moreover, the ethical and philosophical considerations arising from this phenomenon invite us to reflect on our understanding of knowledge, reality, and our responsibilities as scientists and technologists. 1. A paradigm shift in understanding reality. Quantum entanglement challenges our classical intuitions about separability and locality. A notion that particles can instantaneously affect one another across vast distances defies our conventional understanding of space and time. This non-locality suggests a deeper interconnectedness in the universe, prompting philosophical inquiries about the fabric of reality itself. As we grapple with these concepts, we are led to reconsider the boundaries of what we know and how we understand our existence. The implications for determinism and free will are equally significant. The probabilistic nature of quantum mechanics raises questions about the extent to which events are predetermined and the role of human agency in shaping the future. This philosophical exploration invites us to reflect on our values, choices, and the ethical considerations that accompany scientific discovery. 2. Revolutionary technological advancements. The advancements driven by quantum entanglement have the potential to revolutionize technology in ways we are only beginning to comprehend. Quantum computing promises to solve complex problems that are currently intractable for classical computers, unlocking new possibilities in fields such as drug discovery, materials science, and climate modeling. Similarly, quantum communication technologies, particularly quantum key distribution, offer unprecedented security for transmitting sensitive information, addressing the growing concerns surrounding cybersecurity. Quantum sensing technologies, enhanced by entanglement, have applications in diverse areas, from precise measurements in fundamental physics to advancements in medical imaging. As these technologies develop, their integration into everyday life will fundamentally alter how we communicate, compute, and interact with the world around us. 3. Ethical responsibilities and challenges. As we harness the power of quantum entanglement, ethical considerations must guide our actions. The potential for misuse of quantum technologies, especially in surveillance and data security, raises critical questions about privacy and individual rights. Ensuring equitable access to these technologies is essential to prevent exacerbating existing inequalities in society. Moreover, the rapid advancement of quantum technologies necessitates the establishment of regulatory frameworks that balance innovation with ethical responsibility. Policymakers, researchers, and industry leaders must collaborate to create guidelines that promote the responsible development and deployment of quantum technologies. 4. Interdisciplinary collaboration. The challenges and opportunities presented by quantum entanglement highlight the importance of interdisciplinary collaboration. The convergence of physics, engineering, computer science, and philosophy is essential for advancing our understanding and application of quantum technologies. By fostering dialogue among diverse fields, we can develop innovative solutions that address both scientific and ethical challenges. 5. Future directions. Looking ahead, the exploration of quantum entanglement will continue to shape our understanding of the universe and our place within it. Ongoing research will unveil new applications and insights, but it will also provoke further ethical and philosophical inquiries. As we push the boundaries of knowledge, we must remain vigilant in considering the implications of our discoveries. In the coming years, as quantum technologies become more integrated into society, the dialogue surrounding their ethical use will become increasingly vital. Engaging with the broader public about the significance and challenges of quantum entanglement will help cultivate an informed society that can navigate the complexities of the quantum age. 6. Conclusion of a journey of discovery. In conclusion, quantum entanglement represents a remarkable intersection of science, philosophy, and ethics. As we continue to explore this enigmatic phenomenon, we are not merely uncovering the secrets of the quantum world. We are also embarking on a journey of discovery that challenges our perceptions of reality, knowledge, and interconnectedness. The implications of quantum entanglement extend far beyond the confines of laboratories and academic discussions. They touch upon the very essence of what it means to be human in an increasingly complex and interconnected world. By embracing the challenges and opportunities presented by quantum entanglement, we can pave the way for a future that is not only technologically advanced, but also ethically grounded and philosophically informed. As we stand on the threshold of the quantum era, let us approach this new frontier with curiosity and caution, guided by a commitment to understanding the deeper implications of our scientific endeavors. In doing so, we honor the legacy of those who have come before us and lay the groundwork for generations yet to come, ensuring that the benefits of quantum entanglement are shared equitably and that our pursuit of knowledge is accompanied by a profound sense of ethical responsibility. Thank you for watching. We hope you enjoyed today's video. If you did, don't forget to hit that like button and subscribe to our channel for more exciting content. Your support means the world to us. We can't wait to see you back here for our next adventure. If you have any feedback or ideas for future videos, drop them in the comments below. Until next time, take care and stay awesome. See you soon.